we're going to look at the next logical step. We've been talking about different types of equilibria. So we've talked a lot about acid equilibria, but we can also talk about bases. Now, just as there are strong acids, there are strong bases. And you'll notice that they are lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide. You'll note that these fit with our old model of bases, which is what we call the Arrhenius theory. Which is they dissolve to release OH minus, right? So the Arrhenius theory of acids and bases, which we learned in grade 9, we mention it. In grade 10, we learn it. In grade 11, we learn it. Not necessarily by name, is that a base is something that you dissolve in water and it releases OH minus. Remember that? Yeah. Good. But all other bases are weak bases. And for those, we aren't necessarily going to see that they have an OH minus ion that they release. Instead, bases are going to follow this basic thing, which is a base will react with water. Now keep in mind, our definition of a base is such that if this is the base, it must react with an acid. So in this case, if B is some base, the thing that's going to act as the acid is water. Now, what's our definition of an acid again? It's the one that releases the hydrogen. And our definition of the base is that it's the thing that accepts or collects the hydrogen. Good. Which means in this case, if H2O acts as an acid and B acts as a base, H2O is going to give up a hydrogen, and it's going to give it to the base. Now that hydrogen always has what charge? Yeah, so it's going to be BH+. And of course, if water has lost a positive hydrogen, it will be OH with a negative charge. So, and which of these, now going in the other direction, would act as the acid, which would act as the base? Is which would be the base. So we call this the conjugate base. One sec. And what would we call this? The conjugate acid. Good. So, just to review what we're saying here then is, anything that's going to act as a base is going to act as a proton receptor, which means an equilibrium base, a weak base. So when we dissolve it in water, it will act as a base, and water itself can act as the acid, which means water is going to give up an H+ ion. Now this reaction also releases OH- ions, but the base doesn't have to have an OH- ion on it. The OH- ion actually comes from the water. It's the water giving up its hydrogen. It's the water acting as an acid that results in the formation of that OH- ion, the hydroxide ion. Yeah, you had a question.
Why'd you put acid under H2O?
Because it's behaving as an acid. The definition of an acid under Bronsted-Lowry theory is anything that will release H+. And a base is anything that
Receives H+.
Exactly.
Okay.
Very good. So in this case, water is going to release H+, that makes it the acid. The base is going to accept the H+, that makes it the base. And we end up with BH+ as the conjugate acid, because when this reaction goes in the reverse direction, it'll be what gives up an H+. And an OH-, which we call the conjugate base, because when this reaction goes in the reverse direction, it will be what accepts the H+. Does that feel okay? Actually, you're just saying that to shut me up?
No.
Okay, good. Then, just like before, we can define Kb. And Kb is also formulated assuming that the concentration of water is constant. such that, what do we have to put in there? Just like Ka, we're going to ignore water for this. Okay, so the concentration of the conjugate acid, BH plus, times the concentration of OH minus ions, divided by the concentration of the original base. This should feel very similar to what we did with acids, right? Same basic idea, but instead of dealing with acids, which react with water to form H3O plus ions, bases react with water to form OH minus ions, right? But the principle is the same. Does that?
In this case, we're not going to put water.
And again, because we're in aqueous solution and because the water concentration is going to be much higher than the concentration of anything else, we treat that as a constant. That is part of Kb.
Okay.
Yep. How's that feel? Okay? Not too bad? All right, can we try this? NH3 is a weak base. It's not that weak, but it is a weak base. It's known as, does anyone know what this is? Ammonia. Okay, so we're going to make a 0.10 molar ammonia solution. So first, we should always have a chemical reaction. NH3 is going to react with what? Water. And it's going to form what? Yeah.
And OH.
Okay, I like that. Of course, there's something I'm missing on both of those. Yeah, what's the charge on this one? Positive, good. And the charge on this one? Negative. Excellent. Very, very good. And with that in mind, we could write a Kb statement for this. We could write a law of mass action. And on the top, we would have the concentration of NH4 plus and OH minus. And on the bottom? Great. And why not water? Because it's included in the Kb. Very good. What am I going to make to actually sort this out? Yeah, we're going to have to make an ICE table. The initial values, how they change, and what they should be at equilibrium. And we have the concentration of NH3. We have the concentration of NH4 plus. And we have the concentration of OH minus. And I'm not going to worry about water because, again, like we said, we're treating that as a constant. It's part of Kb. Now, what is the initial concentration of NH3? 0.10. What's the initial concentration of NH4? And even though, can anyone tell me, what's the actual initial concentration of OH minus? 1.0 times 10 to the negative 7 in neutral water, right? Remember pH and pOH, but we're never going to actually write that, right? What do we just assume because it works out nicely for us, it'll work out fine? We can treat it as 0. Yeah, unless you're dealing with very, very, very low concentrations of very, very weak things, treating that as 0 is not going to matter, and it's going to make your life a whole lot easier. Now, in the change category, which of these goes up, which of these goes down? This goes up? No, that goes down, and the others go up. And what are the numbers on each of them? Yeah, this is 1-to-1-to-1 stoichiometry, so I can just say 1x, which is just x, and x, which means this will be 0.10 minus x, this will be x, and this will be x. Now, we have to figure out the Ka value. So let's look up the Ka of ammonia, which I gave you a table. It should be at the back page, I think. Yeah. And I said Ka, but I didn't mean Ka. I meant Kb. Whoops. Typo. Yeah.
For the ice chart,
Yep.
aren't you supposed to put a bracket and then the M for
I should. I really should.
Is
Yeah.
it for every single time you make a ice chart?
Yeah, it's not a bad idea, though. To be honest, we're all going to skip it sometimes and we're all going to be nice to each other.
Care?
Would I care? I might care a little bit. Boy, that font didn't come out nicely. I'm sorry about that. This isn't even my table. I stole this table, but that looks terrible. But that's okay. What's the Kb of ammonia? 1.8 times 10 to the negative 5. I will answer your question. I don't want to lose my memory of that number.
I'm not talking to you, Angela. I know. I was
Can we
like,
do the
oh,
same
should I
thing?
sponsor it? I'm
Like we
no,
used to check
I don't
the.
want to.
Yes, we can do a little check here to see if we can make our lives easier. What's that little check? What do we do?
0.
Does 0.10 minus x equal 0.10 question mark? And yes, sorry, go.
0.10 over 1.8 times 10.
Okay, what's that equal? It's going to be, we're dividing it by 2, so it's going to be, I can do this. Ready? I'm going to beat you. 5 point something times 10 to the 3, so this is going to be 5,000-ish.
5,555.
5,555. Is that greater than or equal to 500?
Yes.
Yes. Therefore, instead of writing 0.10 minus x, we can just write 0.10. Does that make sense? So that's going to make our lives easier, because when I go to do this one here, what is the Kb value again? 1.8 times 10 to the negative 5. And that's going to equal, what's going to go on the top here? X and down here we said we can just write it as 0.10. What would our next line be? Next line? Oh, sorry. I honestly just. I'm sorry. Did I get it right? Do we trust me?
Yes.
Are you sure?
No. Yes. Yes, you do.
Cool. Sorry about that. What should I do next? Square root on both sides. Now, of course, 18 doesn't have a nice square root. What's the nearest square root there is 16, right? So this would be 4 point something times 10 to the negative 7. Really? Oh, interesting.
Should I check my answer again?
No, I mean, I trust you. I'm just surprised. Oh, and it should be times 10 to the negative 3 anyway. Times 10 to the negative 3. 1.34 times 10 to the negative 3? Huh. Yeah, not what I was expecting. But you know what? That's okay, team. All right. So there we go. Now, really quickly, by the way, is it true that 0.10, don't write this, minus 0.00134 is still 0.10? Yeah. See how our assumption is fine? Again, you don't have to write that. Now, have we answered the question? No, but we can fill this in. This will still be 0.10, right? What will the concentration of NH4 plus be?
How would that be 0.10?
Because 0.10 minus 1.34 times 10 to the negative 3 equals 0.10. And I'll show that, actually. This will be 0.10 minus 0.00134, which is going to be 0.10. Yep. But of course, we're in 2 sig fig land.
When you rounded 0. Oh, okay, yeah. I'm dumb.
No, you're not dumb. You're the furthest thing from dumb. You're very, very smart. Remember, it's adding and subtracting sig fig rules, right? So even though that goes down, it's still to the number of decimal places. Easy mistake to make. Don't worry about it. What would this be? Yeah, and this one. Okay, now, the question is, what is the pH, right? So, we've done all that. Can we find pH directly? No, because we don't know the concentration of H3O plus, right? We do know the concentration of OH minus is 0.00134, right? So, what would you do here? There's actually a few ways to approach this, and they're all fine. Does anyone have an idea? How can we find the pH here? Okay, pause for a sec. One suggestion I'm being given is find pOH. I like that suggestion, because what could we do once we knew that?
You can minus from 14.
Yeah, you can, which is, you have the same answer, and I like that you said you can minus from 14, and this one went, And I knew them both. Yeah, we're in the right order there. So one option would be find POH, and that's relatively easy. The POH is just calculated by taking what? Negative log of the concentration of OH minus, which is the negative log of, in this case, 0.00134 molar. And that will be, of course, 1, 2, 3. This is going to be 2 point high, like 2.8? 2.9. 2.9? Great. So POH of 2.9. Okay, now that's not the answer to our question. The other thing we know is that pH is calculated by doing what? 14 minus the POH, which means that the pH is 14 minus 2.9, which means that the pH is 11.1. Okay. That is, to me, the easier way to do it. What's the other thing we could have done? Because Kw, which is equal to 1.0 times 10 to the negative 14, equals the concentration of H3O plus times the concentration of OH minus, right? And then we could have said, okay, 1.0 times 10 to the negative 14 equals the concentration of H3O plus times 0.00134. We could have said the concentration of H3O plus is equal to, and divide both sides by that. What would we get? Someone do that for me. Times 10 to the negative 12. And then we could have said, therefore, pH is equal to the negative log of 7.46 times 10 to the negative 12. And that should give us 11.1. Totally up to you. I like the first one better. I think the first one's easier, but it's good to be able to do both. It is, it's good to understand the relationship, right? How's that feel? Not too bad? Be honest. Just bad enough? Anyone find it too bad? You find it too bad. If you need help, please come get it. Yeah. Mm-hmm.
Is it sometimes the E? I'm like,
That's right, yeah. When it says find the equilibrium concentrations, that means E.
So it's
right?
just equilibrium.
It's the equilibrium concentrations. That's what that means. At equilibrium, what will the concentrations be?
Oh, okay.
Does that make sense?
Is it molar?
Sorry?
The answer's in molar.
Yeah, and I mean, it could be, you have a question where it's in millimolar, micromolar, or something like that, but typically it'll be in molar. If you study biology, it's funny, all the university kids coming and getting help with their final papers, which has been really fun and sort of gratifying for me. I should show you, if you think my papers are rude. Let's see if I can find Kyla's. And she's doing an excellent job. Really, I didn't have much help to do here. This is a biology lab.
What year is she?
Third year. But just to show you, this is just one lab for one course. Yeah. Yeah, you bet. Sam? Huh? 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 Not just a pretty face. Not even a pretty face, some would say. So look at this. Lab 4. So this is her fourth lab, just to keep in mind, of the semester so far. That would be a 31-page report. Yeah.
She's wasting her time.
I'll be sure to let her know. So there's her introduction.
Wait,
Looking pretty good. No, it's just a lab report.
She just felt like doing this.
No, I'm sure she didn't feel like doing this. They said, here's a lab, do it, and then write a report.
And she decided, okay, 30 pages.
Well, that's what you got to do if you want to get a decent mark, yeah. Yeah.
How long did she get between F and LBS? How long did she get to?
Third year university, but still, But to be clear, like just to show you like what these things look like,
How long did you run it?
No high school kid.
I don't know, a couple of weeks.
Oh, okay.
But like look and see, like notice beautiful formatting, nice figure titles at the bottom, table titles at the top, calculations. There's the actual data she got from her gel.
Oh, this is.
There's some more data there. Discussion, still discussion, more discussion, discussion still going, still discussion, still discussing, still discussion, still discussing, still discussing, and references.
Whoa, that's nice.
39 references.
Yeah?
Um,
So there you go.
in university, do the profs like, you know how you do trials where like you do like 3 runs or whatever? They don't have that, right?
Like of a paper?
Remember how like when we're like, for example, bio, you let
Like submit, resubmit, submit, resubmit. No, I'm training you to do that. That's the process you have to do yourself. So your version of that is you're going to write it, send it to a friend to edit yours while you edit theirs, criticize it to all hell, take it back, fix it, send it to another friend to criticize it to all hell, take it back and fix it. 'Cause yeah, you're going to submit it and they're going to grade it. Yeah. So anyway, this would be a typical third year lab report. Just if you're wondering.
What is her major?
I think she's biomed.
Ooh, that's what you're doing. You prepared to write 30-page reports?
Yeah.
I'm switched. I can't do that.
But seriously, like that, just so you guys know, if you're ever like, oh, Orlando, he's got such high expectations. Yeah, have at it, guys. Like it's a lot of work. A university science degree is rewarding. It's wonderful. It can lead to a lot of great careers and great jobs and things like that. A lot of work. Lot of work.
Grading in the sense of a professor grading it, or are you just being nicer?
When I grade you guys,
Yeah.
I am grading it like a TA would grade if you do. I think as harsh as a first year TA. So the mark you get in a paper from me should be if you do well with it. Now you're gonna have to slightly modulate because different courses have different expectations. But like if you're writing at that level, the mark I give you in a senior paper here is the mark you'd get in a first year paper.
They teach us how to write it?
No.
Or they just.
This is really helpful.
You should know already.
You should know, which is why I teach you.
Yeah.
Because then they're gonna give you what.
All right, so let's get back to it. All right, so this is KB. I don't actually have another example in the note because they're all the same. It's just like Ka, but instead of working with acids, you're working with. Oh, you guys are good. Okay, there's one other thing we want to talk about, which is solubility. In general, for ionic compounds, they dissolve according to this equation, right? Where we say like, okay, if we have A, B, and we dissolve it, then what we end up with is however many A's we have, aqueous, with plus whatever, and then however many B's we have, right? Also aqueous. That's the general rule of dissolving, right? And the thing is, this is actually an equilibrium, which is the things that are solid will constantly be dissolving, dissociating, and the things that are dissociated will every once in a while be bouncing back together into a solid. Does that make sense?
Yeah.
Okay. So that's actually not so bad then, because we can say, well, we could take the equilibrium constant of this, and we call this Ksp for solubility product. But it's going to be the concentration of A to the exponent of whatever that is, times the concentration of B to the exponent of whatever B is, and it's not going to include this. And why? It's not like the water where it doesn't change. When you dissolve something, that changes completely. It could potentially change a lot. Potentially all of it could dissolve. Why can't we include that in our equilibrium concentration? No, it's not the same thing. It's different things.
Is it like why you can't include catalysts?
Nope, it's used up. Good thinking. It's a solid, which means it doesn't have a concentration. You can't have a concentration of a solid, right? Think about it. Concentration is how many moles are in a given volume. That only applies to things that take the shape of their container, right? Like that fill a volume. A solid doesn't have a concentration. So the solid is not a part of the equilibrium. Note, the solid is not a part of the equilibrium. Now this actually has a really important consequence. It means that how much solid you have actually has nothing to do with how much of it you can dissolve. The only thing that matters is how much is already dissolved. Does that make sense? The amount of salt you put in water, for example, doesn't affect how much it can dissolve. All that matters is how much has already dissolved. Does that make sense? So in this type of reaction, this is going to keep dissolving until it reaches a certain value, until this concentration maxes out at Ksp. And only when it reaches that threshold will the reverse reaction start to kick in substantially, after which time, that's there, yeah.
What does Ksp stand for?
Solubility product. I don't know why the P is product, but that's what it is, yeah.
Remember how like you were, I don't know, for a second, that's how you were talking about like K and then there's like a subscript.
Yeah, the subscript just always tells us kind of what we're talking about.
For like what we've learned so far, are like the main ones we're going to be using is Kb, Ka.
Kb for bases, Ka for acids, Kw for water, Ksp for solubility, and then all the other ones are just kind of there to help us know what we're talking about, but they're all just the same. But these ones are all specific. You have to remember with solubility that the solid is not a part of this, right? Because the solid doesn't have a concentration. Kw is equal to 1.00 times 10 to the negative 14, and it's always equal to the concentration of what?
Oh, is that H3?
H3O plus times the concentration of OH minus, and that's because water reacts with water to form H3O plus and OH minus. Yeah, that was a good question. I'm going to delete that here now because that's going to make no sense if somebody comes back and looks at this note and wonders why were they talking about that at the top of this page. But did that answer your question? Good, it was a good question. Okay, now, functionally then, this will give you the saturation point. Does that make sense? If you use Ksp, it will tell you the most you can dissolve. Does that make sense? It will tell you the highest concentration of A and B that can be achieved in that solution. Does that make sense? Is that okay? Is that logical enough? Okay, so we'll do an example here. We go in the lab and we figure out that in 100 mils of water, we can dissolve 18.8 grams of sodium chloride. And the question is, what's the Ksp? Here we want to find the product. Does that make sense? Well, no problem. Let's write the reaction first. Sodium chloride dissolves in water to form what? Na plus and Cl minus, which means that the Ksp law of mass action equation will just be that Ksp equals what? Concentration of Na times the concentration of Cl minus. Okay. We don't have to do an ICE table because we already know the equilibrium level. Does that make sense? No ICE table necessary because this isn't the initial. This is equilibrium. This is when it's saturated. Does that make sense? So this is actually easy. So all we have to do is calculate the concentration of these. So what's the concentration of NaCl here? Well, concentration is always what over what? How much stuff over how much? Oh, it's been a while since we've done this. Remember that? We did a lot of these in the past, guys. Anytime we want to know concentration, it's a fraction. And on the top, we put how much stuff. And on the bottom, we put how much solution. And we like the stuff in moles, but I don't have the stuff in moles right now. I have the stuff in grams. How many grams? How many grams? 18.8 grams of NaCl. And the bottom should go in what unit? Grams. We eventually want it to be moles per liter. Okay, I can actually do this in liters. Is everyone comfortable with that? What's 100 mils as liters? Nope. 0.100. If you're not comfortable with that, you could just do another step in your dimensional analysis. Does that make sense? But if everyone's reasonably okay with 100 mils being 0.100 liters, we'll go like that. Now, I don't want to talk about grams of NaCl. Where do I put that? On the bottom. What do I want to talk about? Moles of NaCl. How much does a mole of NaCl weigh? Well, the molar mass of NaCl is what plus what? What's the molar mass of sodium? 22.99. That's plenty of sig figs for us, right? And what's the molar mass of chlorine? 35.45. Great. Can someone do that for us? It's obviously going to be 58.44. If that's right, great. If not, tell me what's correct. Is that right? Okay. So we know 58.44 grams is 1 mole. And when we do that math, we should get 188 divided by 58. This should be on the order of 3. 3 point something. Like 3.3, I'm thinking. 3.4? 3.2. Okay, 3.22 molar NaCl. And now we just have to say, okay, well, this is pretty easy. There's 3.22 moles of NaCl. Like, you can just do this in your head. I just want to be really clear. But if you wanted to do it by dimensional analysis, how much Na plus do we get for every mole of NaCl? Yeah, it's 1 to 1. Does everyone see that? That we get 1 mole of Na plus ions for every mole of NaCl. Now, again, you can do this in your head. You really don't have to show this step, but just to show it to you. So what's the concentration of Na plus? 3.22 molar. And then what's the concentration of Cl minus? Again, this one's so easy because it's just 1-to-1 stoichiometry, but I still want to show you the steps so that if you get a tricky one, you know what to do. Does that make sense? So for every 1 mole of NaCl in this reaction, I get 1 mole of Cl minus ions, and so that's also going to be 3.22 molar. Does that make sense? So then, what is the Ksp at what temperature is it? 34 C?
I have a question.
Yeah.
I don't know if this is an obvious answer.
No.
But you know how the starting point of how many moles we have is NaCl is 3.22.
Yeah.
So wouldn't using that is the starting point and it breaks into NaCl?
Yep.
Na and Cl.
Yep.
Right? Why is it the same amount for both?
Great question.
And not
Great question. Nope, great question. Let's say I had, okay, see this thing here? One of these, if I take it apart, gives me 1 lid and 1, what would we call this? Container. 1 lid, 1 container. So if I start with 1 sharpener and I take it apart, I get 1 lid and 1 container. Does that make sense? Great. Let's say I had 322 of these. All right, can you picture that? So I got 322 of these containers. If I take them all apart, how many lids will I have? Great. And how many containers will I have? Did that answer your question?
Yes.
So when we take apart sodium chloride, if you take apart, instead of 3.222, let's just keep it simple. Say we took apart 322 sodium chlorides. How many sodiums would you have? Great. And how many chlorines would you have?
So it's the same with what you just used for the sharpener. It doesn't have to be like equal masses.
it is equal masses, because keep in mind, it is equal masses, right? Because if this weighs 10 grams, right? And let's say this weighs 8 grams, then how much does this weigh? 2 grams. And so if you do that 322 times, I'm not going to do that math in my head right now, but it would work out, right? The masses all add up. Mass is conserved.
Okay.
Did that answer your question? That's a good question, right? Because it's easy to forget our basic stoichiometry when we start dealing with it in weird settings, but this is just basic stoichiometry, right? The other way to say it is, yeah, for 1 mole of this, you get 1 mole of that, right? That's the reaction.
Okay.
Is that fair? Cool. Now remember, Ksp is saying, what is the equilibrium constant? And sorry, this should be written as an equilibrium. What is the equilibrium constant if the most you can possibly dissolve here is 18.8 grams in 100 mils? Does that make sense? And that's what we're working out here. And the way we do that is we say, okay, if that's the most that will dissolve, then that's the equilibrium point, right? Up until then, we actually haven't reached true equilibrium. We've just run out of reactant, right? But once we get to that point, now we haven't run out of reactant. Now we're actually at equilibrium. And now you can keep adding solid salt till you're blue in the face. No more is going to dissolve. We're at equilibrium. There's no more to dissolve. Does that make sense? And now to actually work out the Ksp value of that, well, Ksp is just the concentration of sodium times the concentration of chlorine, which means Ksp is just 3.22 molar times 3.22 molar. And I don't know how your 3.22 times table is. Mine is not the best. So I'd probably use a calculator for that. Obviously, it's going to be more than 9, but kind of like 9. 10.4? Okay. And what will the unit be? Molar squared. Good. Yeah, because molar 3.22 times 3.22 is 10.4. Molar times molar is molar squared. There we go. How's that feel? Hello. Does that feel okay? Now again, it's actually interesting because if you're dissolving salt, if you calculate the concentrations of these before it's saturated, you'll get a value less than this. That's okay. But at this point, it will reach the equilibrium point, and beyond that, you won't be able to dissolve any more salt. Does that make sense? So it will build this value, concentration of Na plus Cl, when you multiply them, it can be lower than this. That's allowed. It can be equal to this. That's allowed, but it can't be higher than this. Because when it goes higher than this, the reverse reaction will kick in, and it will start producing solid salt again. Does that make sense? The reason it's possible to have it not actually equal this, it could be lower, is because you may just not yet have added enough salt for it to reach equilibrium. Does that make sense? Saturation is an equilibrium point, and if you haven't added enough salt, you're not at the equilibrium point yet. Does that make sense? In other words, Ksp is the saturation point. It's actually for product, but I like to think of it as Ksp being the equilibrium constant at the saturation point. Does that make sense? That'll really help you kind of remember. So let's try another one. The saturation point equilibrium value of mercury hydroxide is 3.0 times 10 to the 26. So the molar solubility is just another way of saying what concentration of HgOH2 is the max. What's the most we can dissolve? Does that make sense? Okay. Now this is actually a bit of a tricky question. All right, can we try it out? Okay. Here we are going to make an IC table because it's not telling us the concentration. But first let's make our reaction. If we have HgOH2 and we dissolve it in water, what are we going to get over here? Mercury. And what will the charge be on mercury? Positive what? Can you tell from this equation? It's got to be positive 2. If not, you can check your periodic table. But there we go. We're going to get mercury ions. And what else will we get? 2 OH negatives. Yeah, agreed. How's that? Does that feel okay?
Can you explain why we give it 2 plus? Like, is it 2 plus like 2 extra electrons?
Well, grade 11 chemistry, right? Like, grade 10 chemistry, really. Which is, this is neutral. Like, first of all, just go look at the periodic table. It'll tell you the charge on everything, right? Mercury is one of our polyatomic ions. So you can't just look at the table. You have to look at your periodic table of ions, right? You have to look at the one that gives you the charges. But the other thing is you can just tell from this because we know the charge on OH. What's the charge on OH? -1. If you have 2 of them, how much negative is that? Okay, so what must the Hg be then to balance that out? +2. Good. Does that make sense?
Yeah.
Okay, so that's how we know. Did that answer your question?
Yeah.
Good. And again, listen, it's very easy to forget those older skills. Very easy to forget them. So worth reviewing. You're not, like, whatever. It's not going to cost you 1 million marks in these things, right? But, like, do keep in mind, too, that, like, when you get to university, they do reteach everything. Not everything. They're not reteaching you grade 9, 10, 11 chemistry. A bit of 11. They reteach the tougher stuff in 11 and all of 12. But, boy, it comes quick. Like, I can't speak to other things. I wasn't an English major. I wasn't a French major. But I was a science major. And there is an expectation that you go in knowing this stuff. You know what I mean? So if you go into science next year, definitely spend your summer like brushing up on your 11 and 12 chemistry. If you're going to be taking physics, brush up on your 11 and 12 physics. Because like other people are there are going to know what they're doing and hit the ground running. You don't want to be the guy who hits the ground not knowing what you're doing. It's not a nice feeling. So study. All right. When we go to write our solubility law of mass action, Ksp, what will it be here? Concentration of Hg2 plus times the concentration of... Now, is that a thing? That doesn't exist. No. It's the concentration of OH minus. And then what is the rule for laws of mass action? That coefficient is going to become... Yeah. But there's no such thing as the concentration of 2OH minus, right? And that's okay. Easy mistake to make, again, but just be careful with that, right? The coefficient in a law of mass action becomes the Bueller, anyone? Exponent. Good. Very good. You guys are good. God, in time, you could be great. Okay, so now, here's the problem. We know the value of this. 3.0 times 10 to the 26 equals the concentration of Hg2 plus times concentration of OH minus. How in the heck can I have two unknowns and solve one equation? You can't, can you? Except ICE table. ICE. Okay. Now here, we actually don't have to worry about solid mercury hydroxide because, again, you can't have the concentration of something like that, right? Does that make sense? So, when we start off, before we have dissolved anything, what is the concentration of our two things here? Yeah, of course, we start out with nothing dissolved, right? Now, the concentration of these, are they going to go up or down? Up. And the Hg2, how much does it go up by? X. Now, careful here. What's the OH minus go up by? 2x. So, at equilibrium, the concentration of Hg2 plus is going to be x. The concentration of OH minus is going to be 2x. And now, what can we do with those values? We can sub them in. And we want to make sure we do so carefully, of course, because we're careful people. But we can say 3.0 times 10 to the 26 is equal to, what am I putting in for Hg? Great. And what am I putting in for OH minus? And what should I be careful of here? Like that? Outside the bracket. You guys are good. Which means my next line is going to be what? is equal to 2x squared would be 4. Are we comfortable if I do that all in one step? Or would it be better if we said x times 4x squared? Is everyone comfortable with that? 2 squared is 4. X squared is x squared. And then we can say that means that 3.0 times 10 to the 26 is equal to 4x cubed. What would you do next to solve this? Divide both sides by 4. And of course, we can all do this. That would be 7.5 times 10 to the 25, I hope. Check that. How'd I do? Is it negative 26? I don't think so.
It's positive 26.
Yeah. Yeah, there we go. Even a broken clock's right twice a day, Sunana. This is my day. What would your last step be? If something is cubed, how do you uncube it? You can do the cube root, or if you prefer, you can put it to the exponent 1 over 3. That, of course, means the same thing. I don't think my calculator has a cube root function, so I'm just going to do it to the exponent 1 over 3. Mind you, I do not think that OneNote's calculator is going to like an exponent of times 10 to the 26. My prediction, this will give me no answer. 7.5 to the exponent 25, all to the exponent 1 over 3, and it's going to tell me, oh, it did it. Hey, guys, it did it. All right, so what's our answer? So our answer is 4.2, because we're in 2 sig fig land, right? Times 10 to the 8th power. X equals 4.2 times 10 to the 8th power. And that means 420 million molar. Well, that's very soluble. To be clear, that sounds to me like I made a typo when I wrote that down. Maybe it was supposed to be negative 26. But it doesn't matter, team, because that's the question. We're going to go with it. Does that make sense?
Yeah.
For the record today, I think probably that's supposed to be to the negative, because that seems like an absolutely absurd concentration. But that's okay. So, therefore, the maximum concentration, according to this, of Hg OH2 would be 420, not 1,000, million molar. Highly concentrated.
Is it true or?
No, that can't be true. I mean, maybe it is. I would bet you $6.11 that Sunana is right. Shall we look it up? Especially because mercury compounds tend not to be very soluble. So it's hard to imagine that we're able to dissolve 420 million moles of that in 1 liter of water. That would be, to be clear, mercury also pretty heavy. So we would be talking about billions of grams in 1 liter of water. Can we all agree that's not correct? So maybe we will correct that number and then finish the last. It's only the last 2 lines of the question that would have to change, right? So let's look this up. That's embarrassing. Ksp of HgOH2. Negative 26. All right. Question should be negative 26. So let's change that. Whoopsie. Yeah, that was an absurd number. So listen, nothing's going to change except we're going to have a negative there, a negative there, a negative there. And then when we do this, like you said, that's going to be negative 27, right? And now, when we redo that, what do we get? Just do the math. If you do 3.0 times 10 to the negative 26 divided by 4, it's getting even smaller, right? 3 divided by 4 is 0.75. So that's the equivalent.
Wait, the question is negative?
So what was that? Negative 27? All right. So this will be a more reasonable answer. Sorry again about those guys. Oh, mine will not give that to me in scientific notation. Can somebody say it?
1.96
Times 10 to the negative 1.96 times 10 to the negative 9 is a much better. So that'll be 2.0. So 2.0 times 10 to the negative 9. That makes much more sense. 2.0 times 10 to the negative 9 molar, which means very low solubility. You could work how many grams that is out if you wanted. Does that make sense? You could just convert 2.0 times 10 to the negative 9 moles of mercury hydroxide to grams. Mercury hydroxide weighs about 270 grams per mole. That's just a rough estimate. So that would be, 2 times 10 to the negative 9 times 270 is going to be, whatever. That's going to be 540 times 10 to the negative 9, which is 5.40 times 10 to the negative 7, or 0.000000054 grams. In other words, how much of this stuff will dissolve in water? Functionally none. Does that make sense? Which is why, if you go back and look at our old solubility rules, at our solubility table from grade 11 chemistry, it calls mercury hydroxide insoluble. It's not actually insoluble. Nothing's insoluble. It's just really low solubility. Every ionic compound dissolves, right? It's just how much does it dissolve? And this dissolves not very much. But that's actually important, because if you think, how does water eventually erode rock? Well, it's that every little bit of water that flows over it can dissolve it a little tiny bit. And in the short term, that makes no difference. So you think of water just rolling across a rock and just the rock is still there. But over millions of years, it can erode it away because little tiny little bits at a time will actually dissolve and move away. Does that make sense? And then there's also the actual percussive force of the water. Yeah. Yes. Yep. Is everyone comfortable with that from math rules? That's the same as cube rooting. I tend to get away from the root sign and work with that, but that is the same as cube root. Is that cool? I actually have a belief that if they just never invented this symbol, and from the very beginning you had said the half exponent of 4 is 2, that would be a better way to teach that right from elementary school. That it would help us think of that as unsquaring, But because really, what the hell is that? But what is it? What's that? Why? This we intuitively understand as, oh yeah, that's 3 times itself 2 times. That is, oh yeah, 3 times 3 times 3, right? But that, I don't know. I just don't know what it means. It's like a sad music note. Fair enough.
I was thinking of like a check mark. So scroll up a little bit.
Like a check mark house. Little check mark house. How's that?
For the part where it says in like a balance chemical equation where it says, wait, is it 2 just because it's turned out balanced? Wait.
Yeah, it has to be balanced. Yeah, right? Does that make sense? You've got 2 OH minuses here. So how many do you need to have there? Yep, does that make sense?
I answered this.
Yeah, because you guys are all big old brains. And again, it is very normal. You're all mildly forgetting grade 10 and 11 chemistry right now. It's very normal to mildly forget your grade 10 and 11 chemistry when you have something new in front of you, right? But that is why having really solid foundations is helpful, because then when you're exposed to something new, you're not getting confused by the old stuff. That's not a criticism. That's very natural and normal. It's rather just a reminder of why it's important to study and review and really solidify our basic stuff, so that when we are dealing with something new and scary, you want the basic stuff to really be muscle memory. And for you guys, it mostly is. Your basic chemistry skills are really solid, which is good. But the stronger they are, the more you're going to be able to handle new stuff because the old stuff won't trip you up. Don't stress about it. You'll be fine. You're all going to be fine. Lots of homework here. My advice, do every last bit of it. All right? This stuff, because you know what we're doing tomorrow? We're moving on, right? Like, we're going. Like, welcome to university pace, team. Like, we're just keeping going. We're going to keep on trucking.
Wait, do we have a unit test?
Oh, yeah. Not tomorrow? No.
He said we're moving on.
Yes. Next lesson, not the next unit. But yeah, having said that, like this unit's gonna keep on keeping on, like a bird that flew. So just don't get tangled up in blue. All right. Only 2 to go, but they'll trick you. But they're beasts. They're beasts.
I thought you said our unit test was the 18th.
Thursday next week, right? What did I just say?
Oh,
Did I just lie?
I was confused because I thought you were gonna put the unit test after like the last lesson.
Well, I figure you guys will probably want some time to study. And like much as I would like to just get our last unit started pre-Christmas, like there's probably no utility in that because if we do one lesson on redox reactions and then you all leave for 2 weeks, presumably that's not going to be fresh, right? Yeah.
If we have the pH, POH, and we're trying to find OH, and we have the anti-log of
Yeah, which is what? What's the anti-log? Guys, and you'll actually have this on your formula sheet, but it's worth remembering, we know that the pH is the negative log of the concentration of H3O+, and we know that the POH is equal to the negative log of OH-. So now, what if we want to go the other way? If I know the pH, but I need to get the concentration of H3O+, what do I do? What's the undoing of that? Log means to what exponent do we have to put the number 10? So we can say just put 10 to the exponent of negative pH, and you'll get that. And in this case, if you want to know the concentration of OH-, you would just do 10 to the exponent of negative pOH. Very good. Yep.
what does regular log do?
Log says, so the log, the truth is that every log has a base. The default is 10. But, so if they don't write the base is 10. So that's kind of an arbitrary thing. The log base 10 of, let's say, 1,000 is equal to what? It's equal to 3. Because what this means is, what exponent, this here says, what exponent or what power of 10 equals 1,000. That's the definition, right? So in other words, the way you construct the true statement is that 3 to the exponent 10 equals 1,000. So the way to think of a log is you're saying this number in the other true statement is actually the answer. This number is the base. Oops, I wrote that backwards. What is wrong with me? That number is the power, right? And that number is the base. So it's saying, take this base. What exponent would I have to tack onto it to get this number? Which means you can always write a reciprocal true statement, which is that, oh yeah, this base to that power is equal to the number we were analyzing to begin with.
So did you do log of negative pH? Is that the same thing?
pH is already a log.
Oh,
So if you
okay.
take the log of it again, now you're just getting deeper into the weeds of obfuscating a number. The opposite of taking the log is doing 10 to the exponent of.
Okay.
And then it's 10 to the exponent negative here because we didn't take the positive log, we took the negative log.
Okay.
So we took the log and made it negative, so that negative sign is just undoing that obfuscation. Did that answer your question?
Can you scroll down to the number 3?
Sure. In the KB section?
Right there. So for this one, I found the concentration of OH through like the pH of 10.5.
Yeah, don't overthink it. It's easy. So if you know the concentration of OH, what else do you know the concentration of? Right? Because by definition, assuming there was nothing present to begin with, N2H4 is going to react with water, right? And it's going to give us what? N2H5 plus, right? And OH negative. So what do you notice about these numbers? They're the same. Good. So it's not a sneaky question. Simple question. You know what I miss? I miss when the ruler worked in this stupid thing for some reason. Now it doesn't.
Yeah, I remember it doesn't work.
It just will not work.
When did that
Did you
I don't know.
update your system or something?
I don't know, but it just will. Like it just won't work. It just won't do it. It's
Maybe
just like,
still
hey,
working.
you know what I don't want to do? I don't want to work, and I don't know why. Lazy.
Maybe it quit.
Must be a millennial. Anyway, lazy millennials.
You're a millennial.
Mr. Lando, do you think you could link the stream you did for the lesson 4.3 to
Yeah,
one? I couldn't find it.
I would love to. Hopefully, I didn't forget to